Michigan ZE 544 on Tuesday, April the 15th, 2014.
Thank you very much. Good afternoon. Can I have the overhead, please? Thank you very much. Zoom in, please. Thank you, thank you, thank you. Okay. Good afternoon, everybody. Let's continue our discussion from last time. We started talking about mixer design, and we ran out of time last time. The RF mixer design. And one more time, the mixer can be used, what? Not can be used, is used. Is used for both at the transmitter side and at the receiver side. At the transmitter side, we refer to it as a what? As an up conversion. At the receiver side, we refer to it as a what? As a down conversion. Up conversion means what? From an IF to an RF at the transmitter side. At the receiver side, we call it a what? A down conversion from an RF to what? IF. Or RF directly to the what? To the baseband. Which one is more challenging? Which one is more challenging is at the receiver. Why? It is more challenging than at this transmitter. At the transmitter, the signal to noise ratio is pretty what? High. Why is it high? Because the signal power generated at the transmitter is pretty what? It's pretty high. And the noise is not that much. Did you understand that or not? As opposed to what? As opposed to the receiver, where the signal to noise ratio is what? Is relatively weak. Because the signal, the received signal is weak. Clear? Now, as we will see in just a second, now we already know that the mixer is a what? Is a nonlinear device. A mixer is a nonlinear device. Why do I know that it's a nonlinear device? I know that it's a nonlinear device because it's generating frequency components that were not available at what? At the input. Clear? The mixer, by the way, is a 3-port device. A 3-port device. For example, at the receiving end, this port is what? Is the RF port. This one is the local oscillator port. And this one is the what? Is the output port. By the way, where is this one coming from? This is coming from what? As we will study next week, beginning next week, we will study this is what is referred to as a what? As a VCO. VCO stands for what? A voltage controlled oscillator. Generating the what? Generating the local oscillator. The local oscillator, by the way, we will see that in just a second. The local oscillator is either a what? A sinusoid or it's a what? A square wave, periodic square wave. Actually, as we will see in just a second, any periodic signal here will do. In other words, could it be a sawtooth? It could be a sawtooth. It could be a triangular, as long as it's a what? It's a periodic signal. And we will see why in just a second. And you get the output. So this is the RF, this is the local oscillator, and this is the output. And involves, again, as I told you, shifting the spectrum either upward or downward. So in this case here, for example, this is omega sub RF, which is what? Which is the desired spectrum. It is going to be mixed with what? With ALO, cosine omega LOT, and you end up with what? You end up with the shifting of the spectrum toward what? Toward omega RF minus omega LO, omega RF plus omega LO. This, I need to get rid of it. Clear? And it's not that hard to get rid of this because this is at a what? At a much higher frequency than this one here. Clear? I get rid of this and I retain this one at the receiving end. At the transmitter end, it's the what? The other way around. I need to retain this and I get rid of what? I get rid of this. Now, if you see the equation, V out, notice, by the way I wrote it. I wrote it as a what? As a modulation, where the modulation is both at the amplitude and the what? The phase. Did you get this or not? Okay, I need you to understand this. When we do have the modulation here, let's assume what? Let's assume it's A of t cosine omega RF t plus what? Theta of t. This is the what? This is the amplitude modulation. This is the what? The phase modulation. Now, how do I can write this one? I can write it as A of t cosine phi of t cosine. What is cosine A plus B? Cosine A, cosine B, yes? Minus sine A, sine B. So it's what? A of t cosine phi of t cosine omega RFT minus what? A of t sine phi of t times what? Sine omega RFT. What did I call this one earlier in the semester? What did I call it? I call it the I information, and this one is the what? Is the Q information. Did you get this or not? No response. Did you get this or not? When do I need the I and the Q? Can you tell me, when do I need the I and the Q? When I have what kind of modulation? Phase modulation. You follow me or not? If I have a purely amplitude modulation, do I need an IQ? I don't need an IQ. You understand that or not? Why? Because if I'm using different amplitudes, it's only in the same what? In the same dimension. Yes or no? You didn't get it. Did you get it? No, you didn't. I can see your faces, weird faces. Let's see if you can tell me. What are these? Tell me, what are these? Am I changing the, I want you to see the amplitudes. Is the amplitude changing? Yeah. Are we in the same dimension? So what do I need the IQ for? I need only one dimension, one I. Yes? Now you might tell me, but how about a PBSK? In a PBSK, the phase is what? The modulation is on the phase. Yes? But you could always write it like this. What do you have? A cosine omega naught t, and the other one is what? A cosine omega naught t plus what? Pi. You agree? But A cosine omega naught t plus pi is what? Is minus A cosine what? Omega naught, omega RF. Are you following me or not? Which means, what is the amplitudes? A and what? Minus A. Do I need an IQ? I don't need an IQ. Do you understand what I just said or not? You need an IQ mixing or an IQ modulation and demodulation when you do have a what? A combination of what? Amplitude modulation and what? Phase modulation. If you do have only what? Amplitude modulation, you don't need a what? An IQ. One is enough. How about phase modulation? Do I need an IQ? Yes, I need an IQ. Do you understand that or not? The only case that I don't need an IQ is the trivial case, which is the what? Which is the PBSK. Because in the PBSK, I can write it as what? A cosine, and the other one is what? Minus A cosine. Which means what? I want you to think about it as what? Two amplitudes. One of them is what? Plus A, the other one is what? Minus A. And the phase is not changing. Did you get my point? Yes or no? Okay, good. Now, again, as I told you last time, the mixer is a nonlinear device, which means what? It's a nonlinear device, which means what? The systems that I'm going to use, to generate the IF signal has to be what? Either nonlinear systems or what? Linear systems, but they are time what? Varying. Time varying, which means what? It means switching is involved. Do you understand that or not? Switching is involved. Clear? Clear? Okay, I will show you that in just a second. Oh, now, Leave this one for just a second. This chart should be after these. But anyway, we'll get to it in a minute. What are the design considerations? What are the parameters that we deal with? First of all, we deal with whether the mixer is a what? It's a passive mixer or whether it's a what? Active mixer. An active mixer is one that will provide you with a what? With a conversion gain. Question. What does conversion means? And how do I define the conversion gain? And could it be conversion loss? Conversion loss is when the mixer is a what? Is a passive mixer. A passive cannot provide you with a what? With a gain. It can only provide you with a what? Loss. What do you define? How do we define the conversion gain? So the conversion gain now, be careful when you read the specifications for mixers. Sometimes the conversion gain is given as a ratio of what? Voltages, which means what? It's a voltage gain. Or they are given in terms of what? Power. But you can tell, you can see the difference between one and the other. Are you following me or not? Okay, so the conversion gain, by the way, are they the same? Did you answer my question first? No, you didn't understand my question. Let me write it first. GC is what? The power. Assuming the power gain. Power. What is it? It's PIF divided by what? PRF. Did you get it or not? Yes or no? Okay. PIF divided by what? PRF. Where the power, where P is the what? Is the power. Sinusoidal. Sinusoidal. Clear? What if it was a voltage gain? What do I put in the numerator? I put what? The RMS voltage, yes, divided by what? The RMS voltage of what? Of the IF, divided by what? The RMS voltage of the what? Of the RF. Yes? Will it be the same? Will it be the same? I'm still waiting. I'm not sure. Did you get my question? Did you get my question? Will it be the same? In other words, by the way, I think we discussed this earlier in the semester. We discussed this earlier in the semester. There is no question in my mind, but you forgot about it. When you take about the power gain, yes? Well, by the way, what is the power gain? The power gain is the what? Is the current, for example, current squared times R, or the what? Voltage squared divided by R. Yes? The voltage, the conversion, the power gain and the voltage gain. Are they the same? In other words, since they are ratio, do they give you the same answer? They are not going to necessarily give you the same answer. Why? It will, because you are comparing an input to an output. You need to understand, is the input resistance the same as the what? Output resistance. Are you following me or not? You need to look at what is the loading at the input. You are measuring the power on a what? On the input resistance. At the output power at the output resistance. Clear? So be careful when you see this one here. Okay. Sometimes, by the way, they define also the mixer efficiency. Efficiency. Let's see if you can follow this. It's what? PIF divided by what? PRF plus what? PLO plus what? PDC. What is this PRF, PLO, PDC? The PRF is the power of what? Is the RF input power. The PLO is the what? Is the power from the local oscillator. And the PDC is the power from where? From the power supply. All of them are what? In the denominator, and the numerator is what? It's PIF. The higher the efficiency, what does it mean? It means that some of these powers are converted nicely to what? To an higher power. Which means what? There's not a lot of dissipation in the what? In the mixer itself. Clear? No response. Clear? Okay, good. Now, another one which requires a lot of explanation. I need you to understand it because it causes a lot of what? Confusion in the industry. Which is what? When you talk about noise figures of a mixer, you will see that the specifications will define it as an SSB or a what? DSB. SSB stands for what? Single sideband. DSB stands for what? Double sideband. I will explain to you in just a second. Let me skip it, and then what? I will come back to it. Clear? But what is the point that I'm trying to make? Now, first of all, let me make a point on the conversion gain. In the conversion gain, for mixers, more important than the conversion gain is the what? Is the noise figure and the linearity, rather than what? Conversion gain. In other words, if you are not going to get a lot conversion gain from the mixer, that is okay. Because the gain will come from what? Subsequent IF amplifiers or the what? Or the baseband amplifier. Are you following me or not? If for the mixer, it is more important than you worry about what? You worry about linearity and you worry about what? The noise figure. More important than the conversion gain. Clear? So when we talk about conversion gain, 5 to 10 dB, and again, as I told you, this is only provided that the mixer is a what? Is an active mixer. If it is a passive, you are not going to get any gain. We'll get to the noise figure right now. But I want you to see how high it is. At 12 dB, is that high? Yes? That's pretty high. Are you following? But luckily for us, the noise figure is not the first what? Is not the first device in our receiver chain. It's not the first device, so its effect will become a little bit what? It's rather relatively negligible because of what? Because of the gain of the low noise amplifier. Clear? Okay. But I need you to understand what is the difference between these two. In a minute, I will show you that. Port-to-port isolation. What port-to-port isolation? What ports are important to us? Now, first of all, the local oscillator to the IF. The local in other words, this is the mixer. This is the local oscillator, and this is the what? IF. This leakage, I'm talking about this leakage. Now, you might say, Professor, but the LO is at a different frequency with IF. But could it be close? Could it be close? It would be close to the IF. This by the way, which one do I worry more about? RF to IF or LO to IF? Which one is more damaging? And what kind of damage are we talking about? Remember, how many ports do I have? 3 ports. I am looking, first of all, at what? Leakage into what? Into the IF port. We'll get to the leakage in the RF port. Leakage into what? Into the IF port. We have how many leakages? 2 leakages. The LO leaking into the IF and the RF leaking into the what? IF. Which one is more damaging? The LO is more damaging. Why? Because the LO is generated locally with a high signal power. If the signal power here is large, it might result in what? Saturation of the IF stage, or even the saturation of the what? Of the analog to digital what? Conversion, which is the baseband state. Did you get my point or not? This one is a what? Is a weaker one. Did you get my point or not? Yes or no? We need to worry about this. Now, in a minute, when we get to the circuits for mixer design, we will see sometimes we need the local oscillator to be what? Of high voltage, to drive the transistors into what? To switch them from saturation to what? Not to saturation, sorry. From off to what? On. Generating what? A square wave rather than a what? A sinusoid. Did you get my point or not? Okay, but that contradicts with what? Contradicts with the fact that if this one is high, there is always a possibility that it will leak this. What we would like from our mixer, I don't want any RF to leak to the outside. I don't want any LO to leak to the outside. Such a mixer, which we'll talk about it in a minute, we call it a what? A double balanced mixer. A double balanced mixer. A double balance means what? Neither the RF nor the LO are leaked to the what? Show up at where? Show up at the IF. Neither one of them. If you hear the word single balanced mixer, means what? Either one of them, but not the other. Either one of them, but not the other, will what? Show up at the output. Did you get my point? Now, if both of them show up, we call it what? Unbalanced mixer. This is an unbalanced mixer, and this is terrible. Did you get my point or not? Yes or no? Okay. Now, keep in mind, if the RF signal leaked into the output, then there is a possibility that there are what? Some components here, nearby components, near to the desired signal, both of them leak in here, generating what? generating a signal from the what? Intermodulation component, generating a signal which is what? Which is close to the what? To the DC. That will be harmful in the case of what? In the case of the homodyne receiver, the zero IF receiver. Clear? Okay. Now, then I will show you all of these in just a second. The spurious response, this is what? All of these. Spurious means what? Unwanted signal. Are we going to get all of the components? What are we going to get? Listen to this. Plus or minus MFRF plus or minus what? NFLO, which means what? For M and N, all of them are what? Let me write it here. Plus or minus M. Did we use omega or LO? What are we using? Omega? Omega. Let's stick with the omega. Omega. RF plus or minus what? N. Omega what? LO. Sorry. LO. For what? For M and N integers. Clear? All of them will be showing up. Yet some of them will have what? Little effect. Some of them will be what? Serious effect. Serious effect means what? I need to worry about them. Linearity, again, as I told you, is very important for the mixer. And when you measure the linearity, you talk in terms of what? IIP3. The larger the IIP3 or the higher the IIP3, the more what? The more linear is our mixer. Clear? And I just explained to you what do I mean by single balanced and what? Double balanced. One more time. It's something like this. You will see it in the final true and false. So I need you to understand. When we talk about double balance, means what? Neither the what? Neither the RF
time is 1
nor
o'clock.
the what? LO will show up at where? At the IF port. Neither one of them will show up. Is that good or bad? That's good. Single balanced, one of them will show up. Either the RF or the what? The LO. And the unbalanced is what? Both of them will what? Will show up. Clear? Oh. So what remains is what I need to explain to you, the noise. This is the definition. And again, as I told you, if the input impedance and the load impedance of the mixer are both equal to the source impedance, then the voltage conversion gain and the power conversion gain of the mixer will be what? Will be the same. Do you understand that or not? Yes or no? Because one of them is what? Square, it will become what? 20 log. The other one is what? 10 log. It's the same thing because there is a square. But if the impedances are not the same, the voltage gain and the power gain, the voltage conversion gain and the power conversion gain is in general what? Not the same. Did you get this or not? Because the input is measured based on the input impedance. Clear so far? Okay. Now let's talk about the mixer. Let me use the pad first and then, sorry, the noise figure. Okay. This one is good enough. I want you to see this. No, let me use this better. Double sideband noise figure and single sideband noise figure. Let's start with the single sideband noise figure. What does he assume? The single sideband noise figure. What does he assume? Now listen to me. Please listen to me. When we were talking earlier on this subject, we said that the RF frequency is separated from what? Or distance, displaced from the LO by what? By the value of what? The IF frequency. Yes or no? Either the RF is what? Higher than the LO, which we refer to it as what? Low side injection. Or what? The other way around, we call it what? High side injection. Yes? What do we have on the other side? What did we call the other side? No, you lost me here. Concentrate. This is the LO. This is the what? This is the desired. So this is the what? RF. This is omega. What is this from here to here? That's the IF. Yes or no? What is this? I want you to tell me, what is this? What did I sketch here? What is this? This is the noise in the what? Desired band. Did you get my point? Yes or no? Now, on the other side of the carrier, what do I have? What did we discuss earlier? We have what is known as what? As the image. Yes? In a single sideband, it assumes listen to this. It assumes that there is no image here. No image here, which means what? The image has already been what? Filtered out. If you remember, which is doubtful, if you remember, what comes after the LNA? Before the mixer. Before the mixer, in other words, in the superheterodyne. We are talking about the superheterodyne. This is the LNA. Can you tell me what comes before the mixer? This is what we referred to earlier as the what? The image rejection filter. Did you get my point or not? Image rejection filter means what? Means I am assuming that there is no signal in the image band. Did you get my point or not? Yes or no? But the noise is there. The noise, in other words, I want you to see this. Can you tell me what is this? This is the noise in the what? In the image band. I want you to understand one thing. Listen to me. It's the noise, by the way. And let's assume, how did we model the noise? How did we model the noise? Notice, by the way, we are not talking about the noise generated internally by who? By the mixer. That I will take care of it in a minute. Did you get my point or not? We are talking about what? This is the noise introduced during what? Transmission. How do we model it? We model it as a what? A wide Gaussian noise, an added wide Gaussian noise. What type of spectral density do we have? We have a flat power spectral density. Did you get this or not? Yes? This is the part of the noise which is within the desired band. This is the part of the noise which is within what? Within the image band, but there is no image what? Signal. There is no image signal. There is only what? Image noise. Yes? Now answer me the following question. Answer me the following question. When you mix this with this, what do you get? You get this spectrum shifted toward where? To the IF, along with the noise. Yes or no? How about this one? Also shifted to what? To the IF, which means the noise gets what? Doubled, but the signal did not get doubled. The signal is the same signal. Do you understand? Because there was no signal in here. Clear? Yes or no? The signal did not get doubled. So when you are going to map this, or when you are going to convert it, this is what it's going to be converted to. What is this? What am I sketching? And what is this centered around? Clear? Is the signal power the same? The signal power is the same. Are you following or not? But is the noise power the same? Okay. I want you now to tell me, let's see if you can help me with an equation. What is the, remember by the way, the noise figure is what? How did we define the noise figure? The noise figure is the signal to noise ratio at the output divided by what? Signal. No, the other way around. I'm sorry. The signal to noise ratio at the input divided by what? The signal to noise ratio at the what? At the output. Clear? Okay. Remember one more time. This assumes what? Assumes our receiver is at what? Room temperature. Please do not forget this. Do not forget this. This is assuming what? Assuming receiver at what? Room temperature. Now, let's see if you can help me. Let's see if you can help me. Now, when I say signal to noise ratio, when I say signal to noise ratio at the input, what am I talking about? At the what? At the desired what? At the desired one. Yes? But there is another component of the noise, which is where? From the image stuff. Did you get this or not? Now, answer me the following question. Is there also noise generated internally by the mixer? At what frequencies? the internal noise that is generated by the mixer will also have what? Two components. One of them is at what? At RF. The other one is at the what? At the image. Let's assume they are the same. Let's assume they are the same to make the math simple. Did you get my point or not? What is the total noise? If you look at it from what? From the input point of view. From the input point of view, what is the total noise in there? The total noise is what? Is the noise from here plus the noise from what? Here plus the noise that is generated internally by the mixer. Yes? In which band? In here. Plus the noise that is generated internally by the mixer in which band? In here. Are you following me or not? So each noise, how many components for the noise we will have? 4 components of the noise. Yes or no? All of these components will be multiplied by what? G. Did you get the G? Yes or no? All of them will be multiplied by what? By the G, which is the what? Which is the gain. Because I'm referring all the noise to the what? To the input of the mixer. But so will the signal. The signal also will be multiplied by what? By the G. Which means, what is the output signal power? What is the output signal power? The output signal power is what? Is S times what? Is G times what? SI. Did you get this or not? In other words, SO is equal to what? G SI. Did you get this or not? Yes. Can you raise your voice a little bit? My mixer is generating noise at what?
You have said that the mixer will generate noise at the RF frequency, at the image frequency.
Yeah.
Will it generate noise at the RF?
It will generate noise internally. By the way, I don't know what the model of the noise is. If you assume, listen to me, if you assume that the noise generated by the mixer is also what? White, then it means what? It means that some of it will be what? In the RF, and some of it will be what? In the image. Because it's covering the entire what? Band. It depends on how you model the internal noise generated by what? The mixer, internally. Where is this coming from? It's coming again. If you are using a transistor, which we are show in just a second, it will be generated through the what? Through the ID. Are you following me or not? Remember when we were talking about the noise from the ID, from the drain current, and we saw that it does not depend on what? The frequency. In the previous set of charts. Do you remember this? The drain current does not depend on the frequency, which means what? It's white. If it is white, does it mean that there is portion of the noise generated within the RF? Yes or no? Say something. You are losing me here. Say that again. You can or you cannot? I am not getting. He can or he cannot? Can. Okay. I want you to. Do you remember the last set of charts? The LNA? Do you remember the current, the noise that was generated by the drain current? Was it constant? If it is constant, what does it mean? It means that it is what? It is the same for all frequencies. Yes? Will it be part of it here? Part of it will be here. Will there be part of it here? Will be part of it here. Are you following me or not? Are they equal? They are equal because we are assuming that it's what? Flat. However, other sources of the noise, for example, the gate noise, was it constant or was it a function of the frequency? It was a function of the frequency. In this frequency, there will be different noise than in what? In here, due to the gate. But we always assume that the gate noise is negligible. So don't worry about it. I just want to make the math simple here. That's the only reason I want to make the math simple. Clear? Clear? Okay, good. Help me. Now, what is the noise at the output? What is the noise at the output? Look how I'm going to write it. N-I-D times what? G. What is N-I-D? N-I-D is the what? Is the input noise in which channel? The desired channel. Plus what? N, I, how do I write the image? I, M, G. Are you following me or not? By the way, in a minute, I will show you, I will assume this one is the same as this one, because I'm assuming that it's flat. Did you get this or not? Okay, what is this now? N mix D times what? G. Mix D, I. Sorry, mix I. There is an I. What does this mean? This is the internal noise generated by the mixer referred to who? To the input in which band? In the desired times what? G. Yes? Plus what? Mix, comma what? IM times what? G. Did you get this or not? Yes or no? What is this? One more time. This is the internal noise generated by the mixer in which band? In the image band. Did you get this or not? Why am I interested in the image band? Because all of the noise in the image band will be what? Will be converted down to the what? To the IF band. Otherwise, by the way, if this noise, listen to me, is this noise white? We already know that from the drain current, it is white. But I don't care about other bands. Why? Because when you mix it with the local oscillator, you are going to get what? You are going something which is outside the IF. Did you get my point or not? Yes or no? Now, I want you to understand also one thing about the noise, and I will show it to you probably when we get to the oscillator. No, it's here. It's here. I thought it was with the oscillator. I want you to see something here. If the local oscillator, I will get back to the noise figure in just a second. If the local oscillator was not a sinusoid, it was a what? It was a what? A square wave. Yes, if the local oscillator. Am I generating only the fundamental or its harmonics? I will also generate the harmonics, which means what? It means if there are noise components at the what? At a distance, you do understand what a distance means. Distance means what? In a frequency. At a distance of what? IF. From the what? Harmonics. Where will they be converted? They will be converted to the IF. You lost me here. Did you lose me? You lost me. I can tell you lost me. Listen to me. What are the harmonics of this? The fundamental is what? Omega naught. Omega LO. Sorry. Omega LO. Agree? What is the second harmonic? 2 omega LO. If I have a noise, listen to me. If I have a noise which is what? Flat. In the band of what? 2 omega LO plus or minus IF. Plus or minus IF. Yes? When I mix this noise component with the fundamental, I don't have a problem. Do you understand why? Why? I said because 2 omega LO minus omega LO will be what? Omega LO, which is outside the band of interest. But if I mix the noise, you are losing me here. Are you losing me here? If I mix the noise, which is at what band? 2 omega LO plus or minus IF. If I mix it with the 2 omega LO, what am I getting? I'm getting IF, which means the noise is not only in the desired and in the image, but it goes what? Over all the harmonics. Do you see this harmonic? Now, I want you to understand one thing here. In this example, the noise is what? If you look at this example, this is the what? This is the local oscillator. All of these are what? Noise. It is not white in this case. But does it cover the entire band? It covers the entire band. As they get, what are these, by the way? What are these arrows? This is the what? LO. This is what? Twice LO, 3 times LO, the harmonics. Did you get this or not? As they mix with the noise, all of them will be what? Reflected back to the what? IF. You begin adding the noise. That's the reflection now. Here, 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 here. Yes or no? If you add them, this is how it looks. Did it go up? Did the noise level go up? The noise level went up because the noise did not come only from what? From the desired band and the what? The image band. It came from what? Mixing other noise in different bands with the harmonics of the what? Of the local oscillator. Did you get it or not? Resulting in the noise figure goes a little bit what? Up. Clear? Okay. Let's get back to our discussion. So what is SO over N0? It's what? It's a GSI divided by, yes? What is it divided by? G NID plus what? NIM plus what? G N mix D plus what? N mix image. Clear? No response. Clear? Okay. Can I cancel this with this? Yeah. And so now what is the noise figure? The noise figure, what does it equal to? Now remember, the noise figure is what? The noise figure is the noise figure is SNRI over what? SNR 0. Yes? What will it be? Give it to me. Now let's assume this one, let's make simple. Assume NID equal to what? NIM. And what else do I assume? N mix D is equal to what? N mix IM. Let's make simplicity. And let's assume that N mix D plus N mix IM, we refer to it as what? Just N sub A, which is the what? Which is the added noise internally. Clear? What do I have? What do I have? What do I have here? 2N, and this one is what? 2NA. Every term has what? 2NA, 2NA. Yes? The signal is S0 is equal to what? GSI. So the SI, the noise figure, which is what? The SNI over SNO, which means what? Bring this one here, this one here. What do you get? This is the noise figure. What? Sorry, there's no 2. NA over what? NA over what? 2. I messed up. NA, which is what? This plus this over what? Over NI, which is the input noise. Did you answer where the 2 came from? Where is the 2 coming from? Here. What? I have what? I have 2 here. I have what? 2 here. So when you divide the SNRI over the SNR0, you will have a what? 2. Which means what? What does it mean? It means the NF is at least what? How many dB? 3 dB. This is assuming what? If it's 3 dB, assuming what? Assuming that the mixer is what? It's noiseless. By the way, is the mixer noiseless? How could it be noiseless if we just said that the typical noise figure of a mixer is what? Is roughly between 10 to 15 dB. From this equation, I'm only getting what? 3 dB, which is from this term. Did you get my point or not? Yes or no? Okay. Now, the DSP. Noise figure. two situations here. Listen to the first situation. The first situation in here, it assumes that there is a what? There is an image what? There is an image signal in there. There is an image signal in there. Are you following me or not? In this case here, what will happen? Tell me, first of all, let me show you in the chart. This is the 2 dB that I was just telling you about. This is the single sideband. This is the LO. This, by the way, what is this? Is this high side or low side? This is a what? High side injection. Are you following me now? Whereas the one I showed you was a what? The one that I showed you was a what? Low side injection. Doesn't matter. It's the same thing. This one is empty. The noise has what? Doubled, but the signal did not. Did you get this or not? I want you now to see the double sideband. This is one case. How do you describe this case for me? Can you describe this case for me? Describe it for me. Do we have an image in this example? We don't have an image. Why? Because the RF is double sideband around what? Omega LO, which means what? Omega RF is the same as what? Omega naught. Do you understand that or not? When is this, by the way? When we're dealing with what? With the homodyne receiver. When you want to convert it to the IF, tell me. This, the upper sideband and the lower sideband. The upper sideband and the lower sideband. Will the power be doubled? The upper sideband, remember, the upper sideband and the lower sideband, each one have the same what? Information. Yes or no? Each one has the same power. Will the signal power be doubled? The signal power will be doubled. How about the noise? By the way, when I say the signal power will be doubled, I mean what? The signal power will be the same as this one because you are dealing with the same what? Two bands. It's two bands of the same spectrum. Yes? But does the noise double? No noise. No, the noise is still in the what? It's only the desired noise. Plus the what? Plus the one that was internally generated. Did you get my point or not? Which means what? It means the noise figure of this one will be higher or will be lower than this? It will be lower than this. Why? Because this two, instead of the two, we will have what? We will have one. Did you get this or not? By the way, if the mixer is noiseless, what is the noise figure? In dB, in dB. 0 dB. You follow me or not? But there is no such thing as a what? As a mixer which is what? Which is noiseless. Clear? Is this the only case that we can have? Let's look at the other case. The other case, this is a local oscillator. This is the desired channel. Yes? And this is what? The image. Yes or no? There is a noise here and there is a noise in here. I want you to understand. Do you understand the difference between this one and this one? One more time. Do you understand the difference between this one and this one? In here, there is no image. Why? Because we are dealing with what? With a homodyne receiver. In a homodyne receiver, the omega RF is the same as what? Omega LO. Did you get my point or not? Yes or no? Is this the same as this one? No, it's not. But the signal to noise ratio, sorry, the noise figure will be the same. I will explain to you why is that. By the way, assuming that the image and the signal have the same power, which is also what? An assumption. How will this one be converted down? Tell me, how will it convert it down? Will this one be converted down? To the IF. Will this one be converted down? To the IF. Do we add them? We add them. The signal has what? Double. We have what? Two signal power. Yes? Will the noise be converted down? Will this noise be converted down? Which means what? The noise is also what? Doubled. The signal is also what? Doubled. The ratio is what? Same. Which means what? The ratio is what? 1 in addition to the what? Internal noise that is generated by the mixer. Are you following me or not? Yes or no? This, in other words, this. This one is now the sum of this one and this one. And the noise. Did you get this or not? Both noise will be what? So the noise is double. The signal power is also what? Double. The ratio is what? Is the same. Clear? No response. Clear? No response. What is the point that I'm trying to make? The point that I'm trying to make is the following. When you read specifications for the mixer, be careful when you read the noise figure. Is it double sideband or is it what? Single sideband. Because the value will change. The single sideband is what? Is higher than the what? The double sideband. Did you understand this thing here? What is it? Did you understand this or not? Did you get it or not? Yes or no? Okay. What is this? One more time. By the way, what kind of noise is this? Looks like this. Very close to this. Very close. By the way, this one looks like exponential. You follow me or not? Yeah, I said exponential. I'm sorry. Laplacian. The distribution. Exponential is only for positive. This. Did you take a course in probability? Nothing there. Okay. Anyway, this is Laplacian distribution. But what does it look like? It looks a little bit also like a flicker noise. In a flicker noise, most of the power is concentrated at where? Low frequencies rather than at what? High frequency. So it looks like a flicker noise. The point that I'm trying to make is that, do you understand what these arrows mean? What are these? Why are they arrows? Because I'm looking at which domain? The frequency domain. And these, each one of them is a sinusoid, but at different what? Frequency, harmonic, second harmonic, third harmonic, fourth harmonic. Did you get my point or not? All of them will be what? The noise will be what? Reflected. By the way, how do you get the reflection? In the frequency domain, what are you going to do? You are going to convolve a what? The spectrum in the frequency domain. In the frequency domain. In the time domain, you have what? You have multiplication. In the frequency domain, it will be what? Convolution. What do you get by convolving a spectrum with an impulse? You get the spectrum shifted to where the impulse is located. So in here, do you understand why the peak of this is moved, shifted? Because the pulses are what? Are shifted. I am interested only in the noise within the what? IF region. Did you get this or not? And you can see that the noise has what? Has increased because you have contribution from the tail end of all of these noise components. Clear? God, it took me so long on this. But anyway, that's fine. Did you understand the difference between them? Okay, good. Now, let's get back to the charts. Okay. The isolation, we already know. I just explained it to you. There is, by the way, one major problem with the isolation is when you do have like this. This is what? This is a leakage from the LO all the way to the what? To the input of the low noise amplifier. Why is this one serious? Because this one is strong to begin with. Is it strong to begin with? And you are what? You are gaining it. You are amplifying it. I said gaining it. You are amplifying it. And then what? You are mixing it with itself. You are, especially by the way, this is damaging for what type of receiver? The homodyne receiver. Are you following me or not? The homodyne receiver. For the what? For the heterodyne receiver, this is not a big problem. Why? Because when this one mixes with itself, with the local oscillator, you are going to get DC here. But in a heterodyne, what do you have after the mixer? You do have the IF stage, the channel select filter. The channel select filter will get rid of the DC. Clear? Okay. There is also another one. If this one happens to be as the same as RF, is that you have a leakage all the way to the what? Leakage all the way to the antenna, and it will be what? Radiated back. And even if it is not the same, there is still a possibility that it will what? It will radiate and causes interference to some other what? To some other channels operating in the vicinity of yours. Clear? This various response, I already explained it to you, which is what? Plus or minus MFRF, plus or minus NFLO. Clear? Now, figuring out which one of these components are within the what? Within the band of interest is a little bit what? Tedious. Because there are a lot of what? A lot of integers for M and N. Did you get my point or not? So you usually write a program, an Excel sheet, or use some CAD tools to figure out what? To figure out which one of these is in the interest, is the band interest or not. This we already talked about it earlier. I'm not even going to touch it. Which is what? Which is the leakage in the, this is 0 IF. The leakage, the DC will be what? Offset. Are you following me or not? Resulting in damaging the what? The dynamic range of the analog to digital conversion, because the DC will keep what? Moving up and down, up and down. Okay, and the other one. Okay, let's get into the circuits right now. Mixer topology, nonlinear, multiplier type. Nonlinear means what? The circuit is nonlinear. Multiplier mixer means what? Means a mixer with a what? Time varying characteristic. Time varying impulse response. Clear? Let's start with the nonlinear mixer. We'll get to the charts. Don't write anything. Just listen to me. What do I have? I have a nonlinear component. Preferably of what? Preferably of which order? Square law. Square law, nonlinearity. Why? We will see why in just a second. Square law. What do I put as the input? By the way, I'm going to explain, first of all, the operation to you in a block diagram, and then we will get to the circuit. First of all, in a block diagram. This is a nonlinear device. Can I use a transistor here? A transistor is a nonlinear device. By the way, I can even use a what? A diode, which I'll show you in just a second. Clear? Okay. At the input, I am going to add the RF signal and the what? LO signal. Good idea or not so very good idea? Not so very good idea. Why? We were just talking about what? Isolation. And here, they are not going to be isolated. You are going to add them together. I will show you how to solve this in a minute. Did you get my point so far? Okay. What is the characteristic of this nonlinear? We already know earlier in the semester. V naught of t equal to what? Alpha 0. Maybe at the beginning of the semester I called it A sub 0. Doesn't matter, just a constant. Alpha sub 0 plus what? Alpha 1 Vn of t plus alpha 2 Vn square of t plus blah, 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 blah. Yes? Okay. What is Vn of t? Vn of t equal to VRF cosine omega RFT plus what? VLO cosine omega LOT. Yes? What am I assuming here? Can you tell me in this equation, what am I assuming? I'm assuming that there is no modulation, that the RF signal is a single what? Is a single tone. Did you get my point or not? Yes or no? Now, if it is a single tone, where is the IF? The IF will also be a what? A single tone. In other words, you are not going to have a what? A modulation around the what? IF. Did you get this or not? But this just to show you the explanation of this. So what is V naught of t? Alpha sub 0, which is this. Alpha sub 1, this sum. Notice, by the way, I did not assume that this is equal to this, because that assumption does not make any sense. Do you agree? Why? Why it does not make any sense? This is weak, this is what? Strong. Did you get this or not? Now, but keep in mind always, this VRF actually went through who? The LNA. Did you understand that or not? So it's not exactly the received voltage, but it's the received voltage after it went through what? Some amplification stage through the LNA. Yes or no? Okay, good. This is the square. What is this? This is the first square plus the second square plus the what? The middle term. Yes? Plus dot, 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 dot. Answer me the following question. Is this a DC? Do we get another DC? Do we have another DC? I will have another DC. Where? From the cosine square. Cosine square is what? 1/2 plus 1/2 cosine twice. So the 1/2 with this, that's a DC. You follow me or not? But I don't worry about them. Why do I don't worry about them? Remember, we are talking about what? A super heterodyne, which means what? This is the IF frequency, and the output is a what? Is the IF frequency. I don't worry about this. Do I get second harmonic? Where? From which term do I get the second harmonic? I do square. This term and this term, do I get the second harmonic? Yes or no? Now, I'm not going to get third harmonic if my device is a purely a what? A square law device. But if the device is not a purely square device, then I will get the what? third harmonic, fourth harmonic, whatever, all of these harmonics that I can get. Clear? No response. Yes or no? Okay. Now, do I get intermodulation component? Which term? This term. Cosine, cosine. Cosine, cosine is what? Cosine twice the angle. Cosine what? The sum. The cosine, the sum will be what? Filtered out. So what am I getting? Can you explain to me this? Alpha 2, VRF, VLO. Sorry, my finger was pointing in the wrong direction. This one. To alpha 2 times. What happened to the 2? Cosine, cosine is what? Cosine 1/2, cosine 1. Yes? So the 1/2 cancel with this one. So alpha 2, VRF, VLO, cosine omega RF minus omega LO times T. By the way, it doesn't matter whether it's what? Low side or high side. Why? Because the cosine is a what? An even function. That doesn't matter. Yes? Okay. What is the conversion gain? Tell me what is the conversion gain of this amplifier? Voltage gain. Voltage gain. Did I say amplifier? I'm sorry. Of the mixer. What is the voltage gain? Is the what? Is the amplitude at the what? At the IF, which is what? Alpha 2 times VLO times VRF divided by the what? The amplitude at the what? RF, which means what? At the RF port. Yes or no? And this is VRF. Notice, by the way, in here, whether you take the RMS or whether you take the peak, it doesn't matter. Do you agree? Because each one of them will be divided by what? Square root of 2. So it doesn't matter. Did you get this or not? What am I getting? GC equal to what? Alpha 2 times what? VLO. One more time. If you make VLO high, that will increase the what? The conversion gain. It will increase the conversion gain. But what do you need to trade it with? You need to trade it with is that if there is a linkage between the LO and the IF, and the LO happens to be of a what? High voltage, that might result in subsequent stages of your receiver to be what? Saturated. Did you get this or not? So you need to be careful when you do this. Clear? Now, let's see the circuit. Let's see the circuit. Do we have a MOS here? Don't worry about this. I'll explain this one to you in just a second. This is the what? This, by the way, this circuit is this circuit. So, I just explained this one to you. This one is this one. Are you following me or not? So let me use this one. It's more detail here. I want you to see this. This is a what? This is the NMOS. Yes? What am I going to drive it? I am going to drive it into the what? Saturation. Which means I am going to treat it, I'm going to treat the NMOS as a what? As a trans conductance. Did you understand that or not? Yes or no? Do you remember the equation relating the I and the V? Or did Aaron show you this? This is, what is it? 1/2 Kn prime. Do you remember what Kn prime is? Kn prime is what? Mu n COX. I don't expect you to remember this. What is mu n? Mobility of the electrons. And what is the COX? COX is the capacity of the oxide. Did you get this or not? 1/2 Kn prime of what? W over what? L. What is the W? W is the width of the channel. L is the what? The length of the channel. Times what? VGS minus VT. VGS is what? Is the voltage between the gate and the what? The source. Minus what? VT. The whole thing what? Square. Did you get this or not? What is the thing that I'm looking for? That's square. Is that non-linear? That's non-linear. Did you get this or not? Now, what is VGS? Look at the diagram and tell me. VGS is this voltage between the gate and the what? The source. The source is what? Grounded. What is VGS? VGS is what? VRF cosine omega RFT plus what? VLO cosine omega LOT. Yes or no? Plus what? The biasing voltage. The voltage that bias what? That bias this transistor. Clear? Yes or no? Cannot hear you. If you plug in this term in here, will you get an intermodulation component? At what frequency? At IF minus what? LO. Sorry, at IF, which is what? Which is omega RF minus what? Omega R LO, or vice versa. Did you get this or not? All the others are going to be what? Filtered out. By who? Can you tell me by who? By this tank circuit, which is the what? Which is the L and the C. What is this R? This is the load of the what? Of the next stage. The input impedance or the input resistance of the next stage. This circuit is a tank circuit. What is the center frequency? 1 over what? Square root of LC should be equal to what? Omega? Omega IF. Did you understand that or not? Why? So that all the other harmonics that is generated in here does not go through what? Does not go through this. Does not go through the load. Did you get this or not? What is the equivalent circuit of this? The equivalent circuit of this is this. At resonance, what is this behaving at? At resonance, which is at what frequency? Omega IF. Omega IF is the resonance frequency here. Did you get this or not? What is the impedance here? Infinite, which means what? All of it will come to the load. Yes? At the harmonics, what is this behaving as? Short circuit, which means what? None of the harmonics will come where? None of the harmonics will come to the resistor. All of it will come in. Did you get this or not? Yes or no? Okay, good. Now, so this is a tank circuit. It's again omega IF equal to what? 1 over square root of what? LC. Clear? Okay, and again, its purpose to what? To filter all harmonics. All harmonics, including, by the way, including what? Including the DC. Including the DC. Clear? DC, of course, you could put a coupling capacitor. It will also what? Get rid of the DC. Clear? Good or bad? And by the way, if you do this, if you enter this in here, this is what you get. GC equal to what? This is a conversion gain, voltage gain. A voltage, not a power gain. A voltage gain. Everything is voltage gain. Kn prime over 2 times what? W over L VLO. What does that tell you? What should you make the width? High or, sorry, large or small? The width, not the length. The width. You would make it large. The width you make it large, but the L you need to make it what? Smaller and smaller. The ratio W over L, the larger it is, the gain will be what? Will be higher. Clear? Yes or no? Okay, good. Now, what is terrible about this? Terrible about this is that there is no what? There is no isolation between. Clear? Okay, before we get into this, what is one solution? One solution is to what? Is to put one of them in here. So this one, the VRF in, or the VLO, doesn't matter. The VRF in here, and the VRF in what? In here. I'm going to use what? 2 transistors in this case. Did you get my point or not? By the way, listen to me. Let me ask you a question. Can you input also the VLO here directly? In other words, without using another transistor. It's the same transistor, but you apply the RF to the gate and the LO to the what? To the source. Can you do it? Yes or no? But this one is better. Why? Because this one you have what? You do have 2 transistors. Are you following or not? You are applying what? You are applying the VRF in here. You are applying the what? The VLO in here. Clear? The isolation between the LO and the RF is what? Is better. This is again the tank circuit, and I'm taking the IF from here. Clear? Clear? By the way, every circuit has its own what? Has its own biasing in here. These are 2 different transistors. This one and this one. There's the biasing of this. There's the biasing of that. Clear? Okay. Let me ask a question before we get into the get into another thing. Let's go back to here. Instead of a sinusoidal, could I use any other periodic signal? In other words, square wave. And instead of this, Could I use a square wave? Say something. I can use a square wave. Could I use a sawtooth? But all of these periodic signals needs to be periodic with the same period as the what? 1 over what? Omega LO. Did you understand what I just said? Why? Did you follow me or you lost me? You lost me. You lost me. I can tell you lost me. A periodic signal. Can I expand it in a Fourier series expansion? Into what? Into a DC term, if there is any DC term, plus what? Fundamental. What is the fundamental? It's 1 over the period. Yes? And what is it supposed to be? At LO. Did you get my point or not? At LO. Would I get other harmonics? I will get other harmonics. Did you get this or not? So, as long as what? As long as I use a periodic signal whose period is the same period as the what? As the sinusoid, then I'm okay. Did you get my point or not? Then I'm okay. Now you might say, but Professor, why you are using a periodic signal rather than a sinusoid? We already have an advantage of using a what? A square wave, plus or minus polarity, that it will result in what? The fundamental being a little bit what? Higher than the what? Sinusoid for the same what? For the same peak to peak. Did you lose me? Did you lose me? For the same peak to peak, the square wave will give you a higher, a slightly higher fundamental component. What was it? Do you remember? 4 over what? Pi. A little bit more than the what? Sinusoid with the same what? Peak to peak. Why do you need to say the same peak to peak? You need to compare apples with what? With apples. You cannot compare oranges with apples and stuff like that. Did you get my point or not? Yes or no? Okay, good. So keep that in mind. Does not have to be a sinusoid. Does not have to be a sinusoid. Actually, most of the time, you will see it a what? A square, which means what? The VCO, the voltage-controlled oscillator, is generating a what? A periodic square wave rather than a what? Rather than a sine wave. We'll talk about that when we get to the VCO stuff. Clear? Okay. Do you understand why do they call it a dual gate mixer? A dual gate because what? Because the RF and the RF and the LO are applied to the gates of different what? Different transistors. We refer to them as a what? As a dual gate. Yes or no? Cannot hear you. No response. Cannot hear you. Okay, good. Now, no, before we get to the multiplier based, let's look at what? Let's look at some what? Some diode based. Diode based. Let's see if you can follow me. There are multiple examples here. I will show you only a couple. I let you read the rest. But I need you to understand that you don't need a transistor. You can use a what? A diode. Question. What is the characteristic of a diode? What does the diode look like? Diode. Do you remember this? Yes or no? Now, I understand in the previous electronic courses, you might have represented by what? Like this. Let me ask you a question. Is this linear or is it piecewise linear? This is piecewise linear. This is not linear. Did you get my point or not? We call it what? Piecewise linear. But in reality, this is the characteristic of the what? Of the diode. Are you following me? This is the characteristic of diode. Is it non-linearity? Non-linearity. Let's understand. This is the first one. Single balanced. How did we define single balanced? How did we define single balanced? In a single balanced, either the RF or the what? LO will be what? Will show up at where? At the IF. Did you get this or not? Yes or no? Okay, let's see if you can help me. What am I applying? I am applying the input, which is the RF, to a what? To a transformer. Are you following me or not? The secondary of the transformer is center tapped. Center tapped means what? Means this is what? This is positive, negative. Positive, this one will be what? Negative. And I'm connecting it to what? VLO. By the way, question. What is the, oh, it's written here. I should not, I need to ask you the question. what is the voltage in here? Remember, this one is a 1-to-1. 1-to-1 is from where? From here to here is 1-to-1. Which means what? If the voltage here is VRF, what is the voltage here? Also VRF. Yes or no? Now, then I have a diode in this polarity. This one is in the opposite polarity. Now listen to me.
Professor, we have 5 minutes left.
I just started. Okay, thank you, sir. Didn't I just start? Time goes very quickly. Okay, concentrate. What is the voltage, total voltage in here? It's VLO plus what? VRF. But do you agree that the VRF is negligible? The VRF is negligible. Why? It's a weak signal to begin with. So the VLO is the dominant one. The VLO, let's assume it's a sinusoid. If it is a sinusoid, what does that imply? It means half of the time, this one will be what? On, when this one is positive. When this one is positive, will this one be on? Why will it be on? Because it's what? Forward biased. This one, on the other hand, will be what? Off. When this one is on, which means what? The second half, can you tell me about this? Off. Now, the current, this is the load, by the way. This is the load. The current that goes into RL is either in this direction or it's what? In that direction. Did you get my point or not? Okay, so what do I have? Assume VLO of T is a what? A sinusoid. A sinusoid. The wave with fundamental frequency of FLO. Also assume that the absolute value of VLOT is greater than the absolute value of what? VR of T. What does this mean? One more time. It means that the LO is the what? Is the stronger signal. Clear? For all time. When VLOT is positive, D1 is forward bias, D2 is reverse bias. What is the output voltage? Can you tell me what is the output voltage? Don't look at the equation. You are looking at the equation. What is the output voltage? If this one is forward biased, which means what? A short circuit. Ignore the resistance. Ignore the resistance. It is a short circuit. What is the voltage across this? The voltage across this is what? VLO plus what? VT. Plus VRF. Yes or no? So this is this. Do you understand this? Now, when VLO of T is negative, which means what? The lower half of the sinusoid. Yes? What is the voltage here? The voltage here is what? VLOT minus VRF. Do you understand why it is minus? Yes or no? This one is on this one is this. So it's what? This minus this. Clear? Can I combine this equation and this equation together? What do I get? V out of T, which is the output voltage, is equal to what? VLOT, which is the local oscillator, plus what? VRF of T times what? S of T, where S of T is this. S of T is either what? +1 or what? -1. If it is a +1, what do I get? If S of T is equal to +1, what does it mean? It means that we are dealing with what? VLOT is positive. If it is negative, it means what? Negative. Clear? Question. What is the fundamental, what is the period of this guy? What is the period of this guy? The period of this guy is the same as the period of who? Of the LO. Yes or no? Okay. Now, again, assuming LO, we assume that VLO is a sinusoid, its shape really doesn't matter. What matters is that the fundamental frequency of S of T is the same as what? LO. So now, what do I have? V naught of T equal to what? VLOT, this term, plus what? VRF, which is this, V cosine 2 pi FRFT, times what? Times S of T. Did you get this or not? Yes or no? Now, which is equal to what? VLOT plus what? VR cosine 2 pi FRFT. What is this? Can you tell me what is this? That's the Fourier series expansion of who? Of this guy. Yes? You see, by the way, the fundamental at n equal to 1, this is what? 4 over pi. Yes? Question. Do you see any DC component? Why? This one is a plus or minus 1. Right away, what can you tell me? This VRF cosine 2 pi FRFT or cosine omega RFT will not show up in the output. Why? Why will it not show up in the output? Because there is no what? DC component here. If there was a DC component in here, this component will show up at the output. Yes or no? Oh, but will this one show up at the output? This one will show up at the output. This is by itself. Did you get my point or not? You are losing me? Okay. Yes or no? No means you are losing me. Okay. What is the G? Tell me what is the conversion gain, by the way, or loss. We will see that you are not going to get gain. Explain to me quickly before I run out of time. What is the denominator? The denominator is V square over 2, which is the what? Which is the input RF power. Yes? What is the numerator? Where is the 2V over pi came from? This is the 2V. What happened, by the way, to the 4 over pi? It became what? 2V, because sine, cosine, you are going to get what? 1/2. Yes? So it's what? 2V over pi. What happened to the n? 1, because I'm interested only in the fundamental. 2V over pi, the whole thing. Square divided by what? 2. I'm dividing by 2 because it's the what? The RMS. Yes? This is what I get. 4 over pi square.
Professor, we are out of time.
Yeah. Okay, let me make one come. 4 over pi square, which is how many dB? Minus 4 dB. I'm not going to get a gain. Did you get my point or not? That's why I called what? Conversion loss. Clear? Clear? Did you understand why did I call it single balanced? The LO showed up in the final. LO showed up in the output, but the RF did not show up in the output. Clear? I will show you next time. I run out of time. Next time I will show you some more.
This concludes today's session of EE 544 on Tuesday, April 15, 2014.